right? But I didn't know.
We'll start by
Yeah,
recalling what
but I
we were
couldn't
doing last
see that
time.
from there. I didn't know how to get from the fact I did those two calculations and equate to
Lagrange's
something
theorem.
different.
So let's recall what the statement is. If G is a finite group, and H is a subgroup of G, then the number of elements in H divides the number of elements in G. Okay? This is a statement of Lagrange's theorem. Now, when we started to prove it, last time we defined proof. Last time we defined an equivalence relation on G. On G, let's call it tilde. We say that X is related to Y if Y inverse X belongs to H. Well, define a relation on G. And we show that it's an equivalence relation, right? Define the following relation on G. X is related to Y if Y inverse X belongs to H. Here X, Y are on G. Then we showed is an equivalence relation on G, right? Remember this? Great. Now let's look. Now if I have an equivalence relation, what do I know? I know that my set on which the equivalence relation is defined can be partitioned into a disjoint union of someone say good morning? Yes, sir. Into a disjoint equivalence, into a disjoint union of equivalence classes. Now let X be in G. What is the equivalence class of X under this relation? Just a second. Okay. So it's the set Y in G such that Y is related to X, right? So it's the set Y in G such that X inverse Y belongs to H. Agree or not? Yeah? Everyone? Everybody? Any question on this? Are we good so far? So this is Y in G. So it's all the Y's in G such that Y is equal to XH for some H in H. Agree or not? Everybody, do we agree with this? If X inverse Y is equal to H, then Y is equal to HX. What am I saying? It's equal to XH. Right? Multiply X on the left, and that's what we get. So what this set really is just the set XH as H is in H. Everyone, do you agree with this? Any questions on that? Is it clear? Is this clear? Yeah? Great. So this is just X. Well, we define this as X times H. Basically, this is what it is. You take all the elements in H, and you multiply them on the left by X. Okay. Yes?
But isn't it only some H?
Yeah, but what is the... So it's the all y and g's that can be written in this form. What are all the y's and g that can be written in this form? It's all, if you take all the h and h, and you multiply them on the left. So I mean, you know, maybe if I do it this way, is it clear? Yeah? Good? Okay. I mean, you know, for some h and h, here it's just an index. Is it clear? So any y, any xh, any element of the form xh will satisfy x inverse xh belong to h. Right? Are we good here? Any questions on this? Clear? Yes? Clear? Yeah, great, awesome. Okay. Small definition here. A subset of G of the form XH, H being a subgroup of G, or another notation that I'll use is that H in a subgroup of G is a subgroup of G. It's called the left coset. It's called a left coset of H. Okay? This is just an, we call it a left because you multiply it by x on the left. Okay? Great. Now, hence, G can be partitioned into a disjoint union of equivalence classes. Agreed? So into a disjoint union of left coset. Or in other words, hence into a disjoint union of okay? Any question? Is it clear? So if I have an equivalence relation, the left cosets are the equivalence class, equivalence classes. So I can partition my group G into a disjoint union of equivalence classes. Agree or not? Any question on that? No, we're good? Great. Yes?
I just think that why, how can G be a subset of H, but H is a subgroup of G?
Where? Here? This?
Like, we start off saying that G is a subset of.
Where did I say? A subset of G of the form XH.
Oh, okay.
Okay? Of left cosets of H. Great. First of all, is H a left coset of H or not? Can you find any element that you, when you multiply every element of H, you get the subgroup H back? Identity, right? Note that H is equal to EG times H is a left coset of H. Okay. Now, why can I say that the number of elements of H divide the number of elements of G? Let's see. Let's draw a small picture. And I don't know if it should help, I guess. So I have my group G, it's a finite group. And then I partition it into left cosets. Okay? My first left coset, what is the easiest left coset? H, right? Then I pick another left coset, I will call it x1h, or x2h, x3h, and so on. I'll just call this one xkh. Okay, G is a finite group, so the number of partition is finite, right? The number of cosets is finite. Okay, great. Now, when do I get that this? Yes, sir.
What exactly does this joint mean?
This joint means no two of them intersect.
Okay.
Okay? H is x2h, x3h, and so on. Now, when is the case that the number of elements of H divides the number of elements of G? Yes?
Because all the partitions have the same number of elements, so if you sum them over.
Exactly. So let's say that all the partitions have the same number of elements. So let's say this one has H many elements. This one has H many elements. And this one has H many elements. And this one has H many elements. If I add them up, how many elements do I get? I get on one side, it's K times H, right? Agree? And on the other side, I get G elements because the cosets partition G. If that is the case, I get that the number of elements of H divide the number of elements of G. Is it clear? Any question on this? Yes?
And what is K? Is it like the cardinality of H itself?
No, K is a number of representatives you have.
It's not
How many equivalence classes do you have? K is a very good question. K is the number of equivalence classes.
But it's not directly like the cardinality of G or H.
Well, what could it be? If it would be the cardinal, if this is true, K would be the cardinality of G divided by the cardinality of H. Yeah.
Can any equivalence class be used for this group?
Can be.
Used for the group?
What do you mean used for?
I mean, we're only using the fact that we're partitioning to, we're partitioning to an equivalent class. Why do you have to specifically do the equivalent class with the equivalent equation of x minus 1 y?
Oh, okay, yeah, that's a good question. Why did I pick this relation? I just wanted the equivalence classes to have the same size. And I wanted H to be one equivalence class. That's a good question. I want H to be one equivalence class. And I want all the equivalence classes to be of the same size. It turns out that this relation will give it to you. Okay? This relation out of nowhere, give this to you. Okay, yeah. A lot of proof that we will see, it will just be define an equivalence relation this way. We'll see what happens. We look at the equivalence classes and we see what happens. Very good question. Yeah?
Just to prove my understanding, is that rock shapes then kind of like, that's supposed to be G?
This is G.
Oh, okay.
And these are not very equal, but let's assume I did a good drawing. and they're all of equal size. Okay? So if all of these have equal size, then we agree that the cardinality of H will divide the cardinality of G. Yes? Is it clear, everyone? Everybody, any question on this? Great. Let's prove this. So let x1 is equal to the identity of G, x2, xk be the representatives of the distinct equivalence classes of things. What we will show that all of these have the same size as H. Of course, K is finite here, right? Because G is finite. Yeah? Is it clear? K, G is a finite group, so the number of equivalence classes is finite, right? Great. Now, how do I show that two things have the same size? Two finite sets have the same size?
A bijection?
I can find a bijection from. Do I need to show that all of these have the same size, or I can say that H has the same size as x2H, and the same proof will follow for all the others, right? So we will show that there is a bijection from H to XH. Okay, now here, if I'm working with finite groups, oh no, we'll show that there is a bijection from H to XH. Yeah. Okay, so define a function let f what do I need to send H to?
XH.
Everybody? If I send H to x times little h, do I get a function from H to x times h?
Yes.
Yeah? Everybody? Is it clear? XH, x times big H, is just the set, it's just H left multiplied by x. So this element, XH, belongs here, provided that little h belongs in H. Belongs to H. Great. Is this function injective?
Yes.
Remember, this is a homework question, right? Yeah, you have something similar in your homework.
Yeah, but since we have to prove it's a bijection, all we can
Yeah.
prove is that it's invertible, no?
Yeah, but yeah, exactly. Exactly. If it's invertible, then it's bijective.
And next has an inverse, so you can put the
Yeah,
inverse
so
on
let's
top.
let's do this. So I'll prove. So I'm here tempted to do something with well-defined or not. So there are two ways of proving it. Now one way, well I'll just do it the easy way. Okay. Usually when you work with cosets with equivalence classes, you need to, well not here. If you want to go the other way, but anyways. Let's forget about this. Okay, let f from h to xh. F is injective. So let's prove this. What do I need? Yeah. If f of h1 is equal to f of h2, then xh1 is equal to xh2. Cancel the x's out, and you get that h1 is equal to h2. When I say cancel the x's out, what do I mean? I mean multiply by x inverse on the left, right? Let me do that. X inverse xh1 is equal to x inverse xh2. So h1 is equal to h2. Okay? Now, you know, I want to do it an easy way. I don't want to. Okay, now is this function surjective? It's obviously surjective, right? It's obviously surjective. Agree or not? So, how do I show it's surjective? I mean, I'm tempted to do something else, but that is surjective. Why is that? Let G be in XH, then there exists an H prime in H such that G is equal to X of H prime. Hence, G is equal to F of H prime. Agreed? Are we all good here?
Shouldn't we specifically define what h prime is in order to show that it's always possible?
No,
Say that
because
is x
if G is in
inverse G.
XH, right?
Yeah.
If G is in XH, you can write G as X times some little h in H, right?
Yes.
You just show that it exists. You don't need to just say exactly what it is. I mean, H prime will be X inverse G. I mean, we could do it in another way. So if you want, we can do it another way, but we could do it another way. I don't know, like, yeah, I don't want to do it. I want to define a function from XH to H, and then show it's a well-defined function, and things like that. Now, it's not very, I mean, it's useless in this case, but we can do an example of things like that. Yes? Yeah, okay, we will do an example, okay? Okay, so, I mean, I'll avoid this example because it's not, I mean, you know, if the thing is clear, you should not overcomplicate it, okay? So, now, so F is bijective. So if F is bijective, it means that H has the same size as XH, right? Agreed? So H I mean, I could have just left this and this would be perfectly fine. Yeah. So H has the same size as XH for all X in H. Therefore, what are my representatives?
Isn't it for all x in G?
In G, sorry. Yes, thank you very much. Did I write let X be in G? Did I write here? Well, let X be in G. Therefore, H has the same number of elements as X2H, has the same number of elements of X3H, has the same number of elements of XKH. Now, H, which is equal to EGH, X2H, X3H, and XKH is a partition G, right? G is those two sets, those K sets are all disjoint, right? If you take any two of them, they're disjoint. They have this, and their union is G. Agree or not? This is how I define X1, which is the identity, X2, X3, Xk, are the representative of the equivalence classes, are representative of the equivalence classes. So G these are equal to H, so this is just K times H. Any questions on this? Clear? This is not supposed to be trivial stuff. So if you have a question, please do ask.
That's what you're doing.
Yes.
It says
The
H
X can be anything.
H, comma X.
So in the
You're
case
saying
of
that like H is only equal to the identity, or you're saying that H is equal to like all of
So
them?
all you have to
No,
do
H is only equal to the identity
since X
times
is
H,
limited
right?
X to
Yes.
X, okay, because it can be only X. Yeah, remember it's just the same, so just
Are we good here?
add X to H. So all you need to do is to show that they all do.
Okay, when I first saw this proof,
Okay.
I got nothing from it.
So we wanted to show that it's the H.
So please start to ask your questions. Yes? I did not say they're equal. Did I? I mean,
On the therefore H.
therefore, with absolute values?
Yeah.
Yeah, the number of elements of H is equal to the number of elements of X to H. Yes. Yes, sir.
So absolute value means that it's the size, not the
The size, exactly. Yes, sir.
What's the line after the
Therefore, here, H is equal to EGH. Oh, H and next to H, X3H, X3KH, partition G, and hence G is equal to H plus X2H plus X3H in absolute values. Any questions? Is it clear? Yes, sir.
Does this only prove it for the following equivalence relation? How is this true for all subgroups? Of subgroups of G?
So H is a subgroup of G. Define the equivalence relation. X is related to Y if Y inverse X belongs to G. Right? H was an arbitrary subgroup. H was a subgroup. We didn't fix H to be anything.
You really fix the equivalence relation, so how is this true for all? Is this true for all of these ones?
No, just for this one.
Oh.
For Y inverse X belongs to H. Okay? Yeah? Yeah, so that's a good question. Notice here that this bijection holds for infinite groups. Right? If H and XH are always in bijection, even if H is infinite. But if G is finite, I mean, if G is infinite, you cannot say really the number of elements of H divides the number of elements of G, right? So it's just the divisibility statement only holds for finite groups. Yes. But what's a good question is that you can have an infinite group G and an infinite group H, but this K is finite. The number of equivalence classes is finite, and you've seen one. Okay? Yes, sir. Any questions? Don't hesitate to ask. Yeah?
Like the line where we specify the permutations.
Yeah.
That's like basically means like every one of those that can be written is like an element of each equivalence class or like.
Yeah, exactly. These are x2, x3, xk. I specified that these are the representative, right? Yeah. So you pick an element of each equivalence class. Exactly. Are we all good here? Yes?
Why is that result important?
Well, very good question. If I tell you you have a group of order, let's say 7, could it, a group with size 7, could it have a subgroup of size 3?
No.
No, right? Because the size of the subgroup must divide the size of the group. So it tells you about the subgroups of the group. What possible sizes do you have? What size can you quickly eliminate?
All the ones that are not 1 or 7.
All the ones that do not divide 7. So let's say 8, for example. Can it have a subgroup of size 3? A group of order 8, can it have a subgroup of size 3? No, because 3 does not divide 8. Is it clear? Yes?
Yeah, but if we have only 7 elements, so it's 1 or 7,
It's
but
1 or
square up is only the identity element.
Exactly. So if you have a group with 7 elements, then the only possible subgroups are 1, the identity, and the whole group.
Okay, so the whole group is a subgroup of that.
Yeah, it's a convention. Like yeah, subgroup. Subgroup does not mean strict subgroup. If you have a group of prime size, can it have a subgroup of any size bigger than 1, or itself? No. That's, for example, one implication. Now, what is more interesting is the converse of this. Like if I have a group of size, I don't know, of size n, and if d divides n, do I have a subgroup of size d?
Yes.
That's a question. It turns out to be no. It's not always the case. The converse is not true. But the smallest example is a group of size 12, I think, and it doesn't have a group of size 6. Okay? But we'll see that later. Yes?
What do you mean like a group has a size of a certain amount? Is that like the amount of
Elements.
elements?
Yeah. How many elements does it have? Yeah? We'll see. We'll see. Okay? You mean the order of an element? The order of an element and the size of a subgroup?
You said something like a group of order 8 can have a subgroup of.
Yeah, okay, yeah. So okay, so the next definition is that the number of elements of a group is called the order of the group. Okay? Yeah. But I don't want to confuse you between order of an element and order of a group. Okay? Yes?
Can you remind me of how we originally defined the rules of creating a subgroup?
How do we
Yeah,
define the rules of?
creating a subgroup.
What?
Like, I know a subgroup that must have the same binary
Yeah.
operations and results.
Oh, so it must have the same binary operation. If you have 2 elements in the subgroup, then the product is in the subgroup, right? And then if you have the identity must be in the subgroup, and the inverses are in the subgroup. If you have A is in H, then A inverse is in H. Okay?
And from those it comes that it always has the same issues, right? So that always has to be close to one.
Yeah, exactly. Those 3 properties will tell you that the relation we defined is an equivalence relation. Okay? So the identity belongs to H will give you transitivity. Will give you, reflexivity. Right? Because X inverse X is the identity. Now, AB is in H. This one will give you transitivity, and this one will give you reflexivity. Okay? Okay. Are we good here? Alive? Great. This is a good proof. I think, in every Algebra 1 final exam I've seen, they say state and prove Lagrange's theorem. Actually,
Are you gonna do that?
I don't know. But I mean, it happened a lot in finals. State and prove Lagrange's theorem. Okay. Now, let's give some definitions and some examples. What do I want to say? Yeah. So, the number of equivalence classes. So what are the equivalence classes in this case? The left cosets, right? The number of left cosets of H and G is called the index of H in G. If G is finite, how many equivalence classes do I have? and is denoted by, we denote this by G 2 points H. And if G is finite, how many left cosets do I have? This is just the number of elements of G, the order of G, divided by the order of H. Order of a subgroup means the number of elements in the subgroup. Order of a group, the number of elements in the group. Okay, not to be confused with order of an element.
Wait, could you repeat that?
Yeah, I'll write this down. Everybody, did we write this down? Yeah? Okay. Let me look this up. What time is it? Sorry, what time?
11.
It's 11:11. Okay, so I will talk about. There's one question I think in the homework that gives. I've got a few emails about it. It's question number 4. Okay, so I'll discuss that in like 5 minutes, maybe the last 5 minutes. Okay, if G is finite, the number of left cosets in G of H in G is the number of elements of G divided by the number of elements of H. Okay, definition. The order of a group G is the number of elements of G. Okay, if G is finite. Okay, great. Now there's a corollary of Lagrange's theorem. Corollary of Lagrange's theorem. Let G be a finite group. And let G be in G. Oh, by the way, this homework, also I got few questions on that. I gave you the answer that you need to upload. Okay, I just gave you 4 questions, and these 4 questions, these are the ones that are going to be graded. Okay, and I did it a bit late, so a lot of you might have, most of you have worked the problems that are not due, but that's okay. Okay, it's good if you work this out. Yes.
When do you get the closest maximum?
Today. Yeah. After this course. After the lecture. Okay? It's gonna be, so this homework, yeah, the 4th homework is gonna be a bit long. But
It's already long, sorry.
8 questions.
no, so this one is gonna be like, there is one question that has 7 parts. But just as these 7 parts, it's like 2-3 lines. Each part is 2-3 lines, and each part depends on the others. So it's all
It's
to
a
get you.
progressive exercise.
It's all to to get you used to the things we're doing. I mean, obviously, you see that the homework really relate to the class, right? I'm not giving you stuff that it's useless, right? It's, for example, this bijection thing between you left multiply by a, you get a bijection. You've seen this, and then you will see more. Okay. Okay, so let G be a finite group and let G be in G. Then G has a finite order. Well, this is not the finite order thing, is not a corollary of Lagrange, but and the order of G divides the number of elements in G. Okay, let's prove this. How do we prove this? So first I have to prove it has a finite order. How do I do that? What is the order of an element in G? It's the smallest strictly positive power that gives you,
The identity.
yeah? That gives you what?
The identity.
The identity. How do I show that this number is finite?
It's not infinite.
If G is a finite group, how do I show that this that the order of any element in G is finite? So this is G has a finite order. This is a good argument. This is a cool argument. Consider the following subset of G. We take G to the n as n belongs to n. Okay, so take all the powers of G. You agree that this is a subset of G, right? G is a group. So you know you have this closure under this operation, under this binary operation. So G times G, G times G times G, G times G times G times G, G times G times G times G times G until your breath runs out, are all in G, right? Yeah? Great, so this is a subset of G. Now if G is finite, what can I say about this subset?
It's finite.
It's finite. G is finite. So the subset G to the n as n belongs to n is finite. Now if it is finite, what does it mean? Can they all be distinct? Can all the powers be distinct? Or it must have a repetition?
Must have a repetition by Page's principle.
Right? I mean, suppose that all the G to the n's are distinct. Do I get an infinite set or not?
Yes.
Now, if this set is finite, then this set must contain a repetition. Hence, you agree or not? Like this set must contain two elements that are the same. Otherwise, this set is infinite, which contradicts the fact that G is finite. Agree with this argument or not? Yeah. Then, there exists n1, n2, and n with such that n1 is strictly less than n2 and G to the n1 is equal G to the n2.
Wait, why is that again?
So this set must contain repetitions, right?
Yeah.
So you have two of these elements, because if all of these are distinct, you would have an infinite set. And G is a finite group.
Oh,
You
okay.
cannot have an infinite set of a finite group.
Okay.
Great. So what does this mean? This means that I have two distinct elements, say n1 strictly less than n2, such that when I raise G to the power n1 and G to the power n2, I get equality. Well, let's bring this means that G to the n2 is equal to 1. Is equal to the identity, sorry. Yes?
How do you know that there's repetition? Like, I'm really not getting it.
Suppose that you don't have any repetition. Suppose all of these are distinct. You get an infinite set.
Oh, because n is.
N is infinite, right?
Mm.
Okay? Agree?
It has to be.
Yeah? We see that? Everyone? Do we see that? Yeah?
How do you know that n1 is not equal to n2 though?
So you have a repetition, right? Means that two distinct powers of n, G to two distinct powers of n will give you the same answer. Right? What does repetition mean? It means you have two elements that are equal in the set.
Yeah, but what if g of n, no matter the n, is equal to g? Because that would still make a repetition, but that
G to
doesn't
the
mean
n is equal to
that
g.
doesn't mean that g has a finite order.
No, so g to the n is equal to g. Okay, so if g to the n is equal to g, this means that, what does it mean?
N is equal to one.
Yeah, what can g be? Say if gn is equal to g, means that g to the n minus 1 is g, right?
Yes.
This means that the order of g is less or equal than n2 minus n1.
What does that mean?
This means that when you raise g to some power, you will get 1. You agree with this? Is this statement okay? Is this statement clear, everybody? Consider this set. This is a subset of G. Now, it must be a finite set. So it must contain repetitions. Because if all elements are distinct, then you would get an infinite set. So what does it mean it has repetitions? It means two elements of this group, of this set, are equal. Well, this means that you have g to the n1 is equal to g to the n2 for some distinct powers. Yep.
Okay, okay, this is something that I'm a little bit confused. Why is that if they do not have distinct elements, then it would be an infinite group? That's,
So if all of these are distinct,
yeah.
Then you have the
how many?
whole of
So
them.
g. These are all the powers of g squared, g cubed, g to the 4th, and so on. If all of these are distinct, then you have an infinite list of elements, right?
I mean, what if it was just like g to the 2 and then g to, okay, never mind, I see this.
Okay? Is it clear? Yes.
Because it goes for all n
N2 always
conditions
has to give
and the set of natural numbers is infinite.
Not
So for that subset to be finite, it has its own
Not necessarily. N2 has to be congruent to N1 modulo the order of G. Okay? So N2 minus N1
It does not
will be divisible by the order of G.
distinct, and if they're all distinct, that
Yes.
means there's all the powers. And natural
Yeah, so
is
if under
infinite,
addition,
meaning that
G to the
set
n becomes
infinite
n times G.
contradicts the fact
Yeah.
that it's a subset of a finite.
Okay,
I see.
are we good here? Is this argument clear? Then, if there is a repetition, then I could find N1, N2, and N such that N1 strictly less than N2, and G to the N1 is equal than G to the N2. Great. Now let me pull this on the other side. I get EG is equal G to the N2 minus N1. Agree so far?
Yes.
Okay, then what do I do? Let S, let's use the well-ordering principle. Let S be the set of M and N such that G to the M is equal to EG. S is non-empty. Since N2 minus N1 belongs to S. Agree? N2 minus N1, those are just positive integers, and N2 is strictly bigger than N1. So N2 minus N1 is an integer. So S is not empty since N2 minus N1 is an S. So S has a minimal element. Now what is the minimal element of S? The smallest integer M such that G to the M is E. This is the definition of the order.
Yeah.
Okay? Yeah?
I'm very interested, but like we have 1 minute. Can we just talk about the problem?
Yeah, okay. Okay, yeah. After just I finish this. Okay, so S is a minimal
25,
element.
sir.
Yeah, that's okay. Yeah, so S is a minimal element, and hence G has finite order. Okay? Okay, great. We'll continue the other one next time.
The order of G divides G.
And then G, yeah, we'll continue the other part next time. Okay? Now, problem 4. It wasn't meant to be a very tough exercise.
Well, you did not know, so.
Okay, so let's have a look at this.
My
So what does it say? It says that if I have sigma, if sigma composed with tau is tau composed with sigma for all tau in Sn, then I need to prove that sigma is the identity. You understand what the question says?
Yes.
Yeah.
Okay, now how do I prove this? The best way to go about it is by contrapositive. Of course, n is bigger or equal to 3. So how do we start? I can give you a hint. Let sigma be different than the identity. I will construct a tau such that sigma tau is different than tau sigma. So the idea is that if sigma is different than the identity, it means there exists x1 and x2 in x, right? X is 1 up to n, such that sigma x1 is equal to x2 and x1 is different than x2. Okay? Agree? This is if sigma is different than the identity. If sigma is different than the identity, what does it mean? It means it maps an element of x to another element of x. Right? It's not like just sigma x is equal to x. So it maps an element of x to a distinct element, to another element of x that is different. Like it maps an x1 to an x2 that are distinct. This is clear. Great. Now if n is bigger or equal to 3, let x3 in x be different than x1 and x2. So x3 is distinct from all of these. Actually, we have different idea, and then you have to. Well, I mean,
You have to
let.
what?
I don't know. I mean, it's
We don't know, sir.
let x1, x3, for example. Okay. And I've done half the more than half the problem. Then show that sigma tau is different than tau sigma. Yeah.
But we just did it's not abelian, so the only way to satisfy this is
No, not necessarily true.
that set is not abelian.
That's true, but this doesn't mean that so if an element commutes with all the other elements, that doesn't mean it must be the identity. Right? Take the group of invertible matrices. Okay, and take 2 times the identity. Okay?